Hi guys, tonight we're going to talk about something absolutely mind-blowing. What would happen if all the oceans suddenly lost their salt and became fresh water? I know it sounds simple, but trust me, the consequences would be catastrophic in ways you've probably never imagined. If you enjoy these deep dive sleep stories that explore wild scientific scenarios, hit that like button and subscribe so you don't miss the next one. And drop a comment below letting me know what time it is where you are and where you're listening from. I love seeing how many of you are winding down for the night across different time zones. Alright, let's dive in. Imagine you're standing at the beach tomorrow morning. The ocean stretches before you, waves rolling in rhythmic sets that have repeated for billions of years. You dip your hand in and bring it to your lips, tasting the familiar salt that defines everything we know about Earth's seas. That saltiness, approximately 35 grams of dissolved salts in every litre of seawater, represents the ocean's chemical identity. Now imagine that tomorrow morning, through some mechanism we cannot explain, every ocean, every sea, every saline body of water on Earth becomes fresh. The salt simply vanishes, leaving behind pure water, H2O molecules freed from the sodium chloride and countless other dissolved minerals that have defined marine chemistry since the oceans first formed over 4 billion years ago. The transformation would be instant. The consequences would unfold like dominoes falling in slow motion, each impact triggering the next in a cascade that would fundamentally reshape our planet within days, weeks, and months. What follows is not a distant catastrophe, but a moment-by-moment unravelling of systems so interconnected that we rarely notice them until they fail. The first casualties would be invisible to human eyes but catastrophic for the ocean itself. Marine microorganisms, the foundation of all ocean life, would begin dying within hours. Consider the cyanobacteria genus Prochlorococcus, single-celled organisms so small that 5 million could fit in a single drop of seawater. These tiny beings are the most abundant photosynthetic organisms on Earth, with global populations estimated at 3 octillion individuals, that's 3 billion cells. They produce approximately 20% of Earth's oxygen through photosynthesis, more than all terrestrial rainforests combined. Every breath you take contains oxygen molecules that these microscopic bacteria liberated from water molecules somewhere in the tropical oceans where Prochlorococcus thrives. But Prochlorococcus evolved in saltwater. Their cell membranes, their osmotic balance, their entire biochemistry depends on the ionic concentrations of seawater. Place them suddenly in fresh water and osmotic pressure becomes fatal. Water molecules rush into their cells, following the concentration gradient, trying to equalize the salt concentration inside and outside the cell membrane. The cells swell like balloons filling with water. Within minutes to hours, cell membranes rupture. The bacteria die en masse. 3 octillion cells bursting simultaneously across the world's oceans would create a bloom of organic matter, but there would be nothing left alive to consume it in the normal way. This same fate befalls virtually every marine microorganism. Diatoms, single-celled algae with intricate glass shells made of silica, contribute approximately 40% of ocean primary productivity, fixing roughly 20 billion tons of carbon annually. There are roughly 100,000 species of diatoms, and they're exquisitely adapted to salt water. In freshwater, their osmoregulation fails, dinoflagellates, which number approximately 2,000 species and include both photosynthetic varieties and the species responsible for bioluminescence that makes waves glow at night, face the same osmotic crisis. Marine bacteria that decompose organic matter, recycle nutrients, and form the base of the ocean food web, populations numbering approximately 1 nonillion cells globally begin dying across every ocean basin simultaneously. The death of marine microorganisms removes the foundation of ocean food webs within days. Zooplankton, tiny animals drifting in the currents, depend entirely on phytoplankton for food. A single copepod, crustaceans typically 1 to 2 millimeters long, filters seawater constantly, consuming thousands of phytoplankton cells daily. Global copepod biomass is estimated at several 100 million tons, and they collectively graze approximately 40% of ocean primary production. When the phytoplankton vanish, copepods have nothing to eat. They begin starving immediately. Their own osmotic balance, maintained by specialized organs that regulate salt and water exchange, fails in fresh water. Within a week, copepod populations collapse. Krill, slightly larger crustaceans that school in massive swarms in polar and temperate waters, follow the same trajectory. Antarctic krill, Euphausia superba, has a total biomass estimated at 379 million tons, making them one of the most successful animal species by biomass on Earth. A single blue whale, the largest animal ever to exist, can consume up to 6 tons of krill in a single day during feeding season. But krill are saltwater organisms. Their gills, designed to extract oxygen from seawater while maintaining osmotic balance with body fluids that match seawater salinity, cannot function in fresh water. Krill stop feeding, stop moving normally, and begin dying. Within 2 weeks, the largest animal biomass in the ocean is gone, replaced by countless billions of small crustacean corpses sinking slowly toward the ocean floor. Now the collapse reaches organisms we can see with the naked eye. Small fish that feed on zooplankton and krill, species like anchovies, sardines, and herring, face starvation and osmotic stress simultaneously. Anchovies school in groups numbering millions of individuals. Global anchovy populations have fluctuated wildly due to fishing pressure, but in some years, the Peruvian anchoveta alone has supported catches exceeding 10 million tons annually, making it historically the largest single-species fishery by tonnage. These fish, typically 10 to 15 centimeters long and weighing perhaps 20 grams each, filter feed on plankton. No plankton means no food, but even if food existed, the fish themselves are dying. Marine fish have evolved osmoregulation strategies completely different from freshwater fish. A saltwater fish, like an anchovy, constantly loses water through its gills and skin because its body fluids are less salty than the surrounding seawater. To compensate, it drinks seawater continuously, absorbing water through its gut while excreting excess salt through specialized cells in its gills. This system maintains internal salt concentrations around 9 to 12 grams per litre, much lower than seawater's 35 grams per litre, but higher than freshwater's near zero concentration. When the ocean becomes fresh, the osmotic gradient reverses. Water floods into the fish through every permeable surface. They cannot drink enough to compensate because drinking fresh water only makes the problem worse. Their kidneys, adapted to conserve water and excrete concentrated urine, cannot process the sudden influx. Within days, organ systems fail. The fish die, not from starvation but from drowning in their own tissues, as cells rupture from excess water. Larger fish follow. Tuna, fish that cruise the open ocean at speeds up to 70 kilometers per hour, sustaining that speed through sophisticated cardiovascular systems and warm-blooded muscles, depend on abundant prey. A bluefin tuna weighing 200 kilograms needs to consume approximately 5% of its body weight daily, 10 kilograms of fish and squid. When the prey fish die, tuna have nothing to hunt, and they face their own osmotic crisis. Tuna maintain internal salt concentrations through active transport, constantly pumping ions across gill membranes in an energy-intensive process. In fresh water, this system becomes unsustainable. Within weeks, tuna populations across all oceans begin dying. Atlantic bluefin, Pacific bluefin, yellowfin, albacore, all gone. The open ocean, once filled with predatory fish that could detect prey from kilometers away, becomes eerily empty. Sharks, which have existed for over 400 million years and survived multiple mass extinctions, cannot survive this. There are over 500 species of sharks, from the tiny dwarf lantern shark at 17 centimeters long to the whale shark reaching lengths of 18 meters and weights of up to 21 tons. Sharks use a unique osmotic strategy. They retain high concentrations of urea in their blood, making their body fluids nearly as salty as seawater through a completely different mechanism than bony fish use. This allows them to maintain osmotic balance without constant active transport. But in freshwater, this system fails catastrophically. Urea begins leaching out through their gills. Their internal chemistry destabilizes. Great white sharks, hammerheads, tiger sharks, bull sharks, whale sharks all face the same fate. Within a month, shark populations worldwide are functionally extinct in the open ocean. The death extends to marine mammals. Whales, dolphins, seals, sea lions, all evolved from terrestrial mammals that returned to the ocean over millions of years. They're air-breathing, warm-blooded, and they drink seawater just like fish, extracting fresh water through their kidneys while excreting concentrated salt. A blue whale drinking seawater to supplement the moisture from its prey has kidneys capable of processing and concentrating salt to levels far exceeding seawater salinity. But even these sophisticated kidneys cannot handle the sudden shift. More critically, whales depend entirely on krill, small fish, or squid. When those food sources vanish, whales weighing up to 170 tons face starvation. They cannot migrate to find food because every ocean has the same problem. Within 3 months, whale populations crash. The great migrations that have crisscrossed the oceans for millions of years come to an end. The largest animals on Earth become casualties of chemistry. Dolphins fare no better. A pod of bottlenose dolphins, typically numbering 10 to 30 individuals, coordinates hunting using echolocation clicks that can detect prey at ranges exceeding 100 meters. They have complex social structures, signature whistles that function like names, and cultures passed down through generations. But when the fish disappear, dolphins starve. Coastal populations might survive briefly by hunting in estuaries where fresh water has always mixed with salt, but ocean-dwelling pods have no refuge. Orcas, apex predators that hunt everything from salmon to seals to grey whale calves, face the same extinction pressure. Pods that specialized in hunting specific prey over generations watch that prey vanish. Within 6 months, cetacean populations, some of the most intelligent and socially complex animals on Earth, are reduced to scattered survivors in specialized coastal zones. Now consider the economic catastrophe. Global fisheries harvested approximately 92 million tons of wild fish in 2018, worth approximately $164 billion. This industry employs roughly 60 million people directly, with perhaps another 200 million people, depending on fishing-related industries. When the ocean's fish populations collapse, this entire economic sector vanishes within months. Fishing vessels sit idle in harbours from Reykjavik to Tokyo to Cape Town. Processing plants close. Markets that have sold seafood for centuries shut down. Restaurants that specialised in ocean fish go bankrupt. The supply chain collapse ripples through the global economy. Aquaculture, fish farming that produced another 82 million tonnes in 2018, faces mixed outcomes. Freshwater aquaculture, which raises species like tilapia, catfish and carp, would continue mostly unaffected since these species already live in fresh water. But marine aquaculture, which raises salmon, sea bass, shrimp, and oysters in coastal pens, would face catastrophe. Salmon, though they spawn in fresh water, spend most of their lives in salt water and depend on marine-adapted physiology. Farmed salmon in what is now freshwater ocean would face osmotic stress. Their growth rates would crash, many would die. The Norwegian salmon farming industry alone, producing approximately 1.3 million tonnes annually worth approximately $7 billion, would collapse. Shrimp farming, concentrated in Southeast Asia and Latin America with global production, around 5 million tonnes annually, would be devastated. Farmed shrimp are marine or brackish water species. In freshwater, they cannot survive. Thailand, Vietnam, Ecuador and India, countries where shrimp farming employs hundreds of thousands of people and generates billions in export revenue, would see an entire industry vanish. The social consequences in coastal communities that depend almost entirely on marine resources would be severe. Mass unemployment, food insecurity, social instability, potential mass migration as fishing communities abandon coasts that no longer provide livelihoods. But the human impact extends far beyond economics. Approximately 3 billion people, roughly 40% of the world's population, depend on seafood as their primary source of protein. In coastal nations across Africa, Asia, and the Pacific Islands, fish provides 50 to 80% of dietary animal protein. When ocean fish vanish, these populations face acute protein deficiency. The world would need to replace approximately 90 million tonnes of wild-caught fish with alternative protein sources. Global livestock production would need to increase dramatically, but this takes time. You cannot simply produce millions of additional cattle, chickens, and pigs overnight. It takes 3 months minimum to raise a chicken to market weight, 18 months for cattle. During that gap, hundreds of millions of people would face malnutrition. The nutritional gap goes beyond simple protein. Fish provides essential omega-3 fatty acids, particularly EPA and DHA, that are crucial for brain development and cardiovascular health. These fatty acids are synthesized by marine algae and become concentrated in fish tissues as they move up the food chain. Terrestrial sources of omega-3s are limited and provide different chemical forms that the human body converts inefficiently. The sudden loss of dietary omega-3s would have long-term health consequences, particularly for children in populations that depend heavily on fish. We'd likely see increased rates of developmental delays, vision problems, and cardiovascular disease in the generation born after the oceans changed. Coastal ecosystems would be transformed beyond recognition. Coral reefs, among the most biodiverse ecosystems on Earth, would die completely within weeks. Corals are marine invertebrates that have evolved over hundreds of millions of years in saltwater. They're actually colonial animals, polyps a few millimeters. Across that secrete calcium carbonate skeletons, building the massive reef structures that provide habitat for approximately 25% of all marine species, despite covering less than 1% of the ocean floor. A single coral reef might support 4,000 species of fish, 700 species of corals, and countless invertebrates. The Great Barrier Reef, spanning 344,000 square kilometres off Australia's coast, is the largest living structure on Earth, visible from space. But corals depend absolutely on the calcium carbonate chemistry of seawater. They extract calcium and carbonate ions from seawater to build their skeletons. The process requires specific pH levels, specific ion concentrations, specific salinity. In freshwater, the chemistry is wrong. Corals cannot secrete skeleton properly. More critically, the zooxanthellae, symbiotic algae living inside coral tissues that provide up to 90% of the coral's energy through photosynthesis, are marine organisms. In freshwater, zooxanthellae die. Without their symbionts, corals bleach and starve. Within 2 weeks of the ocean becoming fresh, every coral reef on Earth would be dead. The skeletons would remain temporarily, gradually dissolving in water that lacks the chemical balance to maintain calcium carbonate. But the living reefs, ecosystem engineers that have existed for 240 million years, would be gone. The death of coral reefs would eliminate habitat for millions of marine species simultaneously. Reef fish that depend on coral structure for shelter and feeding grounds would vanish even if they could somehow survive the osmotic stress. Invertebrates that live in reef crevices, cleaner shrimp, sea urchins, sea stars, octopuses, all would die. The biodiversity loss would be staggering. We'd be witnessing one of the great mass extinctions in Earth's history, compressed into a timescale of months instead of the thousands or millions of years that major extinctions typically unfold across. Mangrove forests, which grow along tropical coastlines with their roots submerged in salt water, would face their own crisis. There are approximately 80 species of mangroves globally, covering roughly 150,000 square kilometres. These trees have evolved remarkable adaptations to thrive in salt water. They exclude salt at their roots through ultrafiltration, excrete salt through specialized glands on their leaves, or sequester salt in older leaves that they then shed. They've adapted to fluctuating salinity, can handle both salt exposure and periodic freshwater inundation from rainfall. But they're adapted to salt water as their baseline. If the ocean becomes permanently fresh, mangroves face a sudden environment they're not optimized for. Some species might survive since they can tolerate fresh water, but the ecosystem would be fundamentally altered. The fish, crabs, shrimp, and other marine organisms that use mangroves as nursery habitat would be gone, eliminating the ecological function that makes mangroves so valuable. The chemistry of the ocean itself would undergo profound changes beyond the obvious loss of salt. Seawater is a complex solution containing not just sodium chloride but magnesium, calcium, potassium, dozens of elements in varying concentrations. These dissolved ions affect water's density, its freezing point, its ability to absorb and release heat, its pH buffering capacity. Salt water freezes at approximately -2 degrees Celsius instead of 0 degrees Celsius for fresh water. This means that in polar regions the ocean surface would suddenly be capable of freezing at temperatures that previously left it liquid. Arctic and Antarctic waters, which currently remain liquid even at -1.8 degrees Celsius, would begin freezing as soon as air temperatures dropped below zero. This would trigger rapid ice formation. The Arctic Ocean, covering approximately 14 million square kilometres, would begin freezing solid within weeks during winter. Currently, Arctic sea ice covers about 6 million square kilometres at its minimum extent in September and expands to roughly 15 million square kilometres in March. But that's floating sea ice forming from salt water, which requires colder temperatures and creates ice that's still partially saline. Freshwater ice would form more readily and be completely fresh. Within one winter, Arctic ice extent would likely double. The additional ice would reflect more sunlight back to space, cooling the region further, potentially triggering runaway ice expansion. Antarctica would see similar effects. The Southern Ocean, which circles Antarctica and plays a crucial role in global ocean circulation, would begin freezing more extensively. Currently, Antarctic sea ice extends to about 18 million square kilometres at its maximum in September. With fresh water, that extent would increase substantially. More ice means more reflection of solar radiation, amplifying cooling in a feedback loop. We could potentially trigger a new ice age, not from cooling temperatures but from the altered freezing point of water allowing ice to form more readily. Ocean circulation patterns would be catastrophically disrupted. The global ocean conveyor belt, technically called thermohaline circulation, depends critically on salinity differences. Cold, salty water in the North Atlantic is denser than warmer, fresher water. This dense water sinks in the Norwegian and Greenland seas, diving to depths of several thousand meters. That sinking drives a circulation pattern that moves water masses around the globe. Warm surface water from the tropics flows northward in the Gulf Stream, carrying approximately 1.4 petawatts of thermal energy, warming Western Europe to temperatures roughly 5 to 10 degrees Celsius, warmer than equivalent latitudes in North America. When that warm water reaches the North Atlantic and cools, its high salinity makes it dense enough to sink, completing the cycle. Remove salinity from the equation, and this circulation pattern collapses. Water density would depend only on temperature. Cold fresh water at high latitudes would still be denser than warm fresh water at the equator, so some circulation would persist. But without salinity differences amplifying density gradients, the circulation would be far weaker. The Gulf Stream would slow dramatically or stop entirely. Western Europe, suddenly deprived of tropical heat being delivered by ocean currents, would experience climate conditions similar to Newfoundland or Alaska. London, at roughly the same latitude as southern Newfoundland, would see winter temperatures plummet. Current average January temperatures in London hover around 5 degrees Celsius. Without the Gulf Stream, January averages could drop to -5 or -10 degrees Celsius, similar to Quebec City. The climate shift would make agriculture far more difficult, threaten infrastructure built assuming mild winters, and potentially make some regions uninhabitable. The tropical oceans would experience different problems. Without the transport of heat away from the equator through ocean currents, tropical regions would become even hotter. Currently, the ocean acts as a massive heat buffer, absorbing solar energy at the equator and distributing it globally. If circulation weakens, that heat stays in place. Sea surface temperatures in the tropical Pacific and Atlantic, currently averaging 26 to 28 degrees Celsius, could rise to 32 or 34 degrees Celsius. This would intensify evaporation, potentially increasing hurricane strength and frequency. Hurricanes derive their energy from warm surface water. Each degree of sea surface temperature increase can intensify hurricane wind speeds by several kilometers per hour. Stronger, more frequent hurricanes would devastate coastal regions that are already vulnerable. The Amazon rainforest, which receives approximately 40% of its rainfall from moisture evaporated from the Atlantic Ocean, would be affected by changes in ocean circulation and evaporation patterns. If Atlantic circulation patterns shift, rainfall patterns across South America would shift correspondingly. The Amazon, already under stress from deforestation and climate change, could experience altered precipitation that pushes it toward the tipping point where rainforest transitions to savanna. The loss of the Amazon would release approximately 150 billion tons of stored carbon, further accelerating climate change globally. The pH of the ocean would change dramatically. Currently, seawater has a pH of approximately 8.1, making it slightly alkaline. This pH is maintained by complex chemical equilibria involving dissolved carbon dioxide, carbonate ions, and bicarbonate ions, all influenced by the presence of other dissolved salts. When you remove the salts, these equilibria shift. Freshwater typically has a pH closer to 7, neutral or slightly acidic depending on dissolved carbon dioxide. The shift from pH 8.1 to pH 7 represents a tenfold increase in hydrogen ion concentration. This would fundamentally alter ocean chemistry in ways that would affect any surviving organisms. The loss of ocean salt would also eliminate a critical climate buffer. The ocean contains approximately 50 times more carbon than the atmosphere, about 38,000 gigatons of carbon compared to roughly 850 gigatons in the atmosphere. This carbon exists as dissolved carbon dioxide, carbonate ions, and bicarbonate ions, and the ocean continuously exchanges carbon with the atmosphere. The ocean's ability to absorb atmospheric carbon dioxide depends partly on its alkalinity, which is maintained by dissolved salts, particularly carbonates. Fresh water has much lower alkalinity and reduced capacity to absorb carbon dioxide. With fresh oceans, atmospheric carbon dioxide would increase because the ocean can no longer absorb as much. This would accelerate climate change, potentially pushing atmospheric carbon dioxide from current levels around 420 parts per million toward 500 or 600 parts per million within decades. Coastal cities would face unique challenges beyond the ecological and climatic disruptions. Much urban coastal infrastructure depends on seawater for cooling. Power plants, particularly nuclear plants, use seawater as a coolant. They draw in millions of litres of seawater daily, pass it through heat exchangers, and discharge it slightly warmer. These systems are designed for salt water with its specific heat capacity and corrosion characteristics. Fresh water has slightly different thermal properties and would corrode systems differently. Power plants would need to adjust their operations, potentially requiring shutdowns for maintenance and modifications. Desalination plants, which currently provide fresh water to hundreds of millions of people in arid regions, would become obsolete overnight. Countries like Saudi Arabia, United Arab Emirates, and Israel depend heavily on desalinated seawater. Saudi Arabia produces approximately 3.3 million cubic meters of desalinated water daily, meeting 50% of its freshwater needs. These plants represent billions of dollars in infrastructure investment. When the ocean becomes fresh, they're useless. The economic loss would be substantial, though the need they filled would vanish simultaneously, creating a strange situation where a critical resource becomes freely available, just as the infrastructure to produce it becomes worthless. Marine transportation would be affected in subtle but important ways. Ships float higher in fresh water than in salt water because fresh water is less dense, approximately 1,025 kilograms per cubic meter for seawater versus 1,000 kilograms per cubic meter for fresh water. A container ship that draws 15 meters in salt water would draw approximately 15.38 meters in fresh water. This might seem minor, but for ships navigating channels and harbours dredged to specific depths, those extra centimetres matter. Some ships fully loaded for salt water would suddenly be riding lower in the water than intended, potentially grounding in harbours and channels. Port authorities worldwide would need to resurvey depths and potentially dredge channels deeper. Ballast systems on ships would need recalibration. Ships take on and discharge ballast water to adjust their stability and draft. These systems are calibrated for seawater density. In freshwater, ships would need to adjust ballast volumes to achieve the same stability characteristics. Naval vessels, particularly submarines, would face more serious challenges. Submarines depend on precise buoyancy control to dive and surface. They maintain neutral buoyancy at depth by carefully balancing weight and displaced water volume. The density change from salt to fresh water would require recalculating all buoyancy parameters. Military submarines would need to return to port for extensive recalibration. During that transition period, submarine operations would be severely compromised. The sound propagation properties of the ocean would change. Saltwater conducts sound differently than freshwater, with sound travelling at approximately 1,530 metres per second in seawater versus about 1,480 metres per second in freshwater. This 50 metre per second difference affects sonar systems, submarine detection, marine mammal communication, everything that depends on underwater acoustics. Naval sonar systems calibrated for saltwater would suddenly be inaccurate. The layers of different water densities that sonar operators use to hide submarines or detect targets would shift or disappear. Underwater communications would need complete recalibration. Tourism industries in coastal regions would collapse. Tropical beach destinations that attract millions of tourists annually depend on healthy marine ecosystems. The Maldives, for instance, hosts approximately 1.7 million tourists annually, with tourism contributing roughly 30% of GDP. Visitors come for diving, snorkeling, and pristine beaches surrounded by living reefs. When the reefs die, when the colourful fish vanish, when the water clarity changes due to decaying organic matter, tourism evaporates. The Caribbean, Mediterranean, Southeast Asian islands all would see similar tourism crashes. Millions of jobs dependent on coastal tourism would disappear. The psychological impact on coastal communities would be profound. For cultures that have lived beside the ocean for thousands of years, that depend on the sea for identity and livelihood, the transformation would be traumatic. Fishing villages that have existed for centuries, where skills and knowledge have been passed down through dozens of generations, would suddenly find their entire way of life impossible. The cultural loss would be immeasurable. Languages that have specific words for local fish species, for ocean conditions, for traditional fishing practices, would lose vocabulary as the reference for those words vanish. Indigenous Pacific cultures whose cosmology, navigation, and social structures are intimately tied to the ocean would face cultural crisis as profound as any physical disaster. Scientists would race to preserve what they could. Marine biologists would attempt to save species by maintaining saltwater tanks and aquariums, but the scale would be overwhelming. You cannot preserve ocean ecosystems in captivity. The largest aquariums in the world hold perhaps 30 million litres of water, a tiny fraction of the ocean's 1.3 billion cubic kilometres. You might save a few hundred species in artificial environments, keep genetic material frozen, preserve DNA samples, but the vast majority of marine biodiversity, perhaps 90% of all ocean species, would be lost within months. It would be one of the great extinctions in Earth's history, comparable to the Permian-Triassic extinction that killed 96% of marine species 252 million years ago, but compressed into a year instead of unfolding over thousands of years. Eventually, life would adapt. Freshwater species from rivers and lakes would begin colonizing the now fresh oceans. Freshwater fish like carp, catfish and bass could potentially expand into coastal areas. Freshwater algae and plants could colonize shallow areas. Over thousands or millions of years, evolution would fill the vacant niches. New marine ecosystems would develop, but they'd be fundamentally different from what existed before. They'd be less productive, less diverse, less complex. Freshwater ecosystems generally have lower biodiversity and productivity than marine ecosystems. The new fresh oceans would likely never match the biological richness of the saltwater oceans they replaced. The deep ocean would become anoxic. Currently, ocean circulation brings oxygen-rich surface water to depth, maintaining oxygen concentrations sufficient for life even at depths of 11 kilometers in the Mariana Trench. This circulation depends partly on salinity-driven density differences. Without it, deep water would stagnate. Oxygen would be consumed by decomposition of the massive pulse of organic matter from billions of tons of dead marine life, and it wouldn't be replenished. The deep ocean would become a dead zone, anaerobic and lifeless, except for specialized bacteria that survive without oxygen. This would persist for thousands of years, until new circulation patterns eventually brought oxygen to depth again. The thought experiment reveals just how fundamental ocean salinity is to Earth systems. That salt, accumulated over billions of years as rivers carried dissolved minerals from rocks to the sea, isn't just a characteristic of seawater. It's a crucial component of planetary functioning. It drives circulation patterns that regulate global climate. It maintains the osmotic environment in which marine life evolved. It affects ocean chemistry that buffers atmospheric carbon dioxide. Remove it and you trigger cascading failures across biological, chemical and physical systems. We take ocean salinity for granted. It seems like a permanent feature, unchanging and inevitable. But this thought experiment reminds us that Earth systems, while resilient on geological timescales, operate within specific parameters. Push them outside those parameters and stability breaks down. We're currently conducting a different but equally dangerous experiment by adding carbon dioxide to the atmosphere, acidifying the ocean by altering its chemistry, warming the planet and disrupting circulation patterns. The consequences might unfold more slowly than instant freshening of the oceans, but the principle is the same. We're pushing a complex system toward conditions outside its evolved tolerance range, and the results will be catastrophic if we don't change course. The ocean's salt is a reminder that the seemingly permanent features of our world are actually the result of billions of years of processes reaching equilibrium. That equilibrium can be disrupted. The salt could theoretically be removed by processes we barely understand. More realistically, we're disrupting ocean chemistry in other ways through pollution, warming, and acidification that threaten marine life almost as severely as removing the salt entirely. The lesson is clear. Respect the complexity of Earth systems, understand that they operate within specific boundaries, and recognize that our actions have consequences that ripple through interconnected systems in ways we're only beginning to comprehend. The oceans are salty for profound reasons, and they need to stay that way for life on Earth to continue as we know it.